Hello, today I'm going to try to walk you through as quickly as possible electrostatic charge. So this is in the electric field section of Unit 4. Version of these notes are online, of course. April 28th is when we probably should have done this class. And I'm going to recommend, typically we'd be doing lots of demos in this if we were in our classroom. So I would recommend that you watch this video from Walter Lewin, MIT professor. He does really good lectures. This lecture is based on first year university students, so it's not really above your guys' level. Usually first year classes are grade 12 version 2 for a lot of courses. So please recommend watching this. It is about 45 minutes long, but it's once you sit down and start watching it, it's actually it's really good. Other things to maybe look over and read over if you are interested, there's a textbook online, chapter 20. It's not a bad thing to read, and it really solidifies some of these points. So I'll try to be quick. This shouldn't be new to you. Atoms exist. Atoms consist of a nucleus. Inside the nucleus is a bunch of protons and neutrons. Protons are typically positively charged. Neutrons have no charge. Together, they're typically known as nucleons, because then it's not distinguishing either or, but so protons are kind of important from this point forward. And outside of the nucleus, that's where the electrons are. Electrons and protons have equal but opposite charge. Protons are positive, electrons are negative, but they both carry the base fundamental charge, otherwise known as the elementary charge, E. So E at this point, this is not the E in your calculator. That E is a number to represent the minimum charge that we're aware of. They were aware of when they came up with that definition. Eventually quarks were discovered, and that kind of threw a little curveball into our basic definition of the smallest charge we can have. But as far as you are concerned, for grade 12 physics, elementary charge is the smallest charge you really can have. When you get into particle physics and learn more about quarks in detail, you can pretty much disregard what I just said. So things that you probably already know about charge, there's positives, there's negatives. What physicists know about charge is they exist, but we don't know why. It is literally, it's one of those questions that nobody has an answer for yet. It's a fundamental characteristic of certain subatomic particles. That's all we can say about charge. It exists. We know it exists. Most charges, most things on that we're aware of are neutral. We can have charge, so we know although everything has charge, most objects are neutral. Again, look at the periodic table. That has all the matter that we're aware of. Everything on the periodic table is neutral until they become ionized. But that's a chemistry class. You can get into that later. And we know also, another key point here, electrons are the things that do the moving. Protons do not. Protons are inside the nucleus of an atom. That's where they're going to stay. So the protons typically don't move. Again, if we get into particle physics, you can pretty much explain why there are scenarios where we can make that something other than, but you don't have to worry about that. So there are three fundamental laws of electric charges. We know like charges repel. If you have two positives together, they're going to push away from each other. We know two negatives are going to also push away from each other. So there is some kind of force that tends to push them apart. And we know that opposite charges attract. So basically that's your big plot to pretty much every romantic comedy movie out there. So positives are attracted to negatives. So that's essentially how almost all chemistry works, and all chemical bonds become a thing because the negatives are attracted to positives. Chemistry doesn't exist without physics. Take that, Mr. McVeigh. We also know that neutral objects are attracted to charged objects. And that is mainly because of something known as polarization of the charges. So here's what that basically means. Here's a neutral object. I've got a neutral object here. For every positive, there's a negative. So you can pretend that means for every proton, there's an electron associated with it. And I just kind of drew a grid of positives and negatives. If I have some charged rod here, so let's just say it's a positively charged rod, it's missing electrons, right? Because electrons are the things that do the moving. So maybe I took the electrons out from whatever method I have. If I bring this rod nearby, what's going to happen is this overall neutral object, the electrons are going to move closer towards this charged object. So overall, this object is still neutral. And so when I bring those electrons nearby, what it does is it creates this area here where I have an overall negative charge, and therefore you're going to have some attraction. You're going to have this body is going to be attracted. It might even move depending on how heavy this is. It's going to move towards the charged rod. And on this side here, it's going to be positive. All right, so you are going to get some attraction. Now, likewise, if I don't have this set up, but if suppose I have a negative, suppose this charge is negatively charged, this rod is negatively charged, and I bring that nearby. So use your imagination for a moment. Maybe I'll just turn it over. So if I bring this rod nearby, and suppose that this was negatively charged, what would happen is these electrons, these negative charges here, would move away, and you'd still get an attraction. Right? Again, this is still neutral, but now we have these negatives on the other side, so it's polarized. It has flipped over. It's negatives over there, positives over there. So again, if this was the negative end, we'd still have an attraction between a positive and a negative charge. So neutral objects are still attracted to charged objects. Okay. And one of the ways that we would play with this in class, you guys would grab some electroscopes. Electroscopes are a very fundamental, really simple thing to kind of show that charge exists and just to play around with some fundamental charges. All it is typically some kind of non-conductive container, so glass, if you will, with little metal leaves. So you can probably build one of these at home if you want, with just a glass jar and some aluminum foil that you probably have lying around. And these are very, very light. And of course, you might build this with a little piece of strong copper wire. When I strong, I meant thick, and set it up so that you have a little bit sticking out. So this is all one continuous conductive piece of material like copper. And so what happens is when it's neutral, so here we go, I have an animation. Look down to the bottom left corner of the screen. When it's neutral, all the charges are balanced out. So if every positive has a negative, I have 5 positives and 5 negatives balanced throughout this neutral electroscope. If a charged object, as you can see from the animation now, if a charged object is brought near, what happens is it's going to, just like that other slide about polarization, when you bring that charged body nearby, what it does is the negatives, so the electrons that are actually in the little ball at the top, they are encouraged to move away because they are repelled by a like charge. So the electrons move down, and what you have is the little tiny foil, little leaves, the metal leaves, if you will, they will diverge. They will spread apart because down below, where all the electrons are, we have too many electrons or too many negative charges, and like charges repel. There's still the odd positive in there, but the negatives outnumber the positives, and so you have a repelling force. And again, you can kind of see this animation. This is basically what you'd be playing with in class, where you'd notice that, hey, every time you bring this charged object nearby, it displaces all the, in this case, negatives. And down below, because these are very, very light in mass, they get displaced very easily. Obviously, if it was way too heavy, gravity would kick in and they wouldn't be charged enough to move. So there's a couple of ways in which you can pass charge on. So where did that negative charge rod come from? Well, it can come from one of 3 ways: friction, conduction, or induction. Friction you guys have experienced. There's a little GIF I stole from the old interwebs. This lady, this little girl, has a terry cloth blanket on, and it's probably winter time, which means the air is a lot drier, which means there's usually a lot more options for when you rub 2 materials together, such as what she's doing right now with her little Shih Tzu. She creates a static charge. She has more than likely taken a bunch of the dog's electrons around all the little hairs, and now the dog has an overall positive charge. And because little tiny hairs of this dog are very, very light individually, they're all positively charged and they don't want anything to do with each other. And so they're just spreading themselves out because they're trying to repel away from each other. And then you have that little static look, which you probably have experienced if you've taken off in the middle of winter a wool sweater and you have longer hair and your hair gets all staticky, and you can even hear the static sounds as you touch it and try to flatten it down. So odds are good you've experienced something like this. So friction is just the rubbing of two materials together. Even non-conductive things like a glass rod, for instance, the glass is terrible at conducting any kind of electricity, but it doesn't mean you cannot add or remove electrons to it. It just means it's going to hold on to them and really not let them spread out throughout. So when you have something like that, basically when you rub two objects together, the heat that it generates makes it easier for certain um, for some of these charges to pass from one to the other. And whether or not you're going to end up with a positive rod versus a negative rod, or maybe this cloth ends up being positive, I know the image is negative, really comes down to the triboelectric series. Some things are more willing to hold on to the electrons. Some things are more willing to give up the electrons. So things like fur, animal fur, hair, they will lose the electrons. They'll say, I don't need these things, you can have the electrons. Whereas things like plastic, acrylic, they're more willing to take the electrons when you rub two things together through friction. So you guys have probably experienced that with a rubber balloon before. You blow up a balloon, not even, I don't think most balloons are rubber anymore. Most of them are probably this polystyrene or polyethylene. But either way, when you blow up a balloon and you rub it against your hair, the balloons are typically going to be negatively charged and your hair is going to be positively charged, and your hair might stand on end because now your head is mostly positively charged. And then, of course, you walk over to the wall and you stick the balloon to the wall. So this isn't something you have to memorize. It's just a little chart that exists to give you an idea of whether or not things are going to be positive or negative. And so that's also how you can say, oh, this thing here should be negative. Well, how do you know? Well, triboelectric series will basically tell you, or you can do experiments for yourself. So that's friction. The other way in which charge can be spread is by conduction. Well, really, friction involves conduction as well, but conduction just basically means two things are touching. So if you have a grounded, that little symbol here, this little triangle means it's grounded. If you have a grounded electroscope, that basically means all the electrons are balanced out with protons, or negative and positive charges are equal. If I would touch an electroscope with something that's negative, like a negatively charged rod, physically touching it, half of these negative charges would spread out throughout this electroscope. Through conduction, typically, whatever was charged will lose half of its overall charges, because charges, again, do not like each other if they're the same type of charge. If it's negatively charged, all these negatives are looking to spread out as much as possible. It's like, I don't like the other negatives, I need to get out of here. And so half of these charges would spread out throughout, and then that would create an overall negative charge for this electroscope. And of course, you wouldn't notice that at the ball. You'd notice it at those little tiny leaves at the bottom, which are very light and therefore able to spread out. And that tells you that it's overall charged. Another thing that can pass charges on are electrostatic induction. So induction is often what people would just call it. So again, if you start off with neutral, every negative is equal to a positive. And this is kind of what that little GIF was a few slides ago. If you bring something negatively charged, you're going to have a little bit of polarization. The electrons or the negative charges move away from the ball because obviously there's other negatives around and it doesn't like that. So of course they will spread down into the bottom there. Their leaves would spread out. You would have some diverging going on. And this overall electroscope is still technically neutral. So if you ground it, in other words, if you touch it either with your finger or just connect it to another kind of cable, the electrons or the negative charges go, hey, look, we have a path where we can get out. So of course they would escape, and therefore you would have an overall neutral system again. So when you ground anything, either electrons are going to escape from your system or they're going to enter the system, because they say, and by they, you know, the powers to be, it is said that Earth has an infinite number of charges, whether it's negatives or positives. But for the most part, since it's mostly the negatives that move, if you ground something and your object is positively charged, the negative charges would race in and balance that out. Whereas if you have an overall, you could technically call this whole system overall negatively charged. If you combine the rod, those electrons are looking for a path to spread out so they can get away from the other negative rod. And so it would see that as a chance to go into the ground and find some different positive charges to be around. So if you ground that with this rod nearby, you would notice the leaves would go back to normal until you took your finger away and you no longer had it grounded. And when you take your finger away and the electric and the charged rod, you'd be missing electrons, because when you ground something, electrons were able to escape. So once you remove that grounding and that bar, you're missing electrons. And so what you do is, through electrostatic induction, you've created an overall positively charged electroscope. So that's just something that you can do as far as passing charge. So friction, conduction, induction. All right. So that's just some things that you would have played with. If you watch that Walter Lewin video, he kind of goes through a bunch of demos. You maybe get a better understanding if you actually watch that. Otherwise, just Google electroscopes, and probably someone on YouTube will walk you through that with a demo they have. But as far as what you need to know, charge is a fundamental property of matter. I usually associate it with similar to mass, in the sense that mass is a fundamental property of matter. Charge is a fundamental property of matter. With mass, you can use little m and capital M, and we all know it means mass. With charge, it's the same thing. You can use little q to denote that it's a charge, or you can use capital letter Q. It doesn't really matter, one or the other. Why is Q chosen for charge rather than C? Reasons. I don't have any. It's just a symbol. So we use the Coulomb to measure the quantity of charge. Big capital C for Coulomb, named after the Frenchman who came up with the whole measuring system for charge, Charles Coulomb, in the 1700s-ish. Don't remember the year. I'm bad with years. So 1 Coulomb of charge. At that time, they thought that was going to be the base amount, but turns out that's very, very wrong. 1 Coulomb of charge actually has 6.24 times 10 to the 18 electrons, so it has a lot of electrons. Kind of thought at the time that 1 Coulomb would be a small charge. Turns out it's really not. 1 Coulomb of charge is very, very, very charged. Your basic elementary charge, so the single charge of an electron or the single charge of a proton, would be, well, you just do the inverse of 6.24 times 10 to the 18, and you end up with 1.602 times 10 to the negative 19 coulombs of charge. The only difference between the proton and electron is the electron is negative, but in magnitude, they have the same value. Okay, so the little tiny e that I mentioned earlier on in this little video, it has a numerical value of 1.602 times 10 to the negative 19 coulombs. Sometimes people just call it 1.6 times 10 to the negative 19. Typically, with a lot of the word problems that you'll be doing, if you do a bunch of them, this number was used to get your result. So if you just use 1.6 times 10 to the negative 19, you'll see that sometimes your numbers aren't exactly lining up with the answer in the back of the book. So just use that until you're told otherwise. Other things to note. So again, the electron has a charge. So here's some masses as well if you want. The electron has a charge of just -1. So very often, instead of calling it the value 1.602, negative 1.602 times 10 to the negative 19, it's often just represented as negative E. The proton is often just left as positive E because it is a constant after all. Then there's other things like alpha particles. Alpha particles are pretty popular when you talk about anything with respect to astrophysics or just particle physics, because alpha particles are essentially a helium nucleus that are able to freely move around. They'd be missing their electrons, and therefore they'd have an overall charge of +2, or 3.204 times 10 to the negative 19, which is a lot easier to be stated as 2 times your base fundamental value, so 2e, which brings us into the math. To calculate the charge of anything, you just need to know how many electrons you have in excess or how many electrons you're missing. If you have extra electrons, because again, it's the electrons that are doing the moving, if you have too many electrons, you're going to have an overall negative charge. If you're missing electrons, you're going to have a positive charge, because when you're missing electrons, then you have more protons on your body or your mass or whatever it is we're talking about. So the equation is pretty simple. You just need to know the number of elemental charges that are either excess or deficit, extra or missing. So for instance, if you had some kind of a capacitor, and a capacitor is just an object that can hold on to charges, and suppose it has 4.5 billion elementary charges, so whether or not it has extra electrons or whether it's missing 4.5 billion electrons, doesn't really matter at this point. We're just trying to get a handle on this equation. So 4.5 billion would be your number. It's a counted value. So 4.5 times 10 to the 9. So that's what billion is. It's just a matter of working it through, walking it through the equation. Q is equal to NE. So if you know the number of actual charges, you just take the number and you multiply by the actual constant, 1.602 times 10 to the negative 19 coulombs, big capital C, not lowercase c. Lowercase c is the speed of light. This is a unit. Coulomb, I should have mentioned this earlier in the video, the coulomb cannot be broken down any further. Coulomb is a very fundamental base unit. All right, it's a property of matter. So if you just multiply those two numbers together, and again, you're going to be using a lot of scientific notation in the future, so try to make sure you get that sorted out in your calculator. If you work that through, you should end up with about 7.2. I'm just going to stick with two figs because that's what was given. 7.2 times 10 to the negative 9 coulombs, and 10 to the negative 9 also means nano. So you can use prefixes with your value, with your coulombs. So expect to see nano a lot, micro a lot, so 10 to the negative 6. I haven't seen milli too often. Usually nano and micro are very, very common when it comes to calculating charge. Sometimes you won't have any prefixes there, but if we're talking about realistic situations, nano and micro are very common. Sometimes you might be calculating the number of charges that are there, missing or extra, and so it'd just be a matter of, so in this question here, if an object has 4 coulombs of charge, I'm getting ahead of myself, talking too fast, very sorry. If an object has 4 coulombs of charge stored, how many elemental charges are present? So it would just be a matter of manipulating the equation Q is equal to NE. Well, you just say N is equal to Q divided by E. So you just need to know how much charge you have and then just divide it by the base fundamental. Whether it's electrons or protons, it doesn't really matter. You're not often looking for a positive negative in this case. And you would just work out the math. You should get something like that. I won't walk you through that. Sometimes you could be looking for an overall change in charge. So again, most objects are neutral, but you can pass charge from one thing to another. Some things will gain charges, electrons, some things will lose electrons. So if they, as I said before, if they gain electrons, they're going to be negative. If they lose electrons, they'll be positive. So that'll bring us to our last example, and then I'll quickly stop this video. How many electrons must be removed from a charged pair of wool socks? So wool is pretty good at passing charges. With a -1 microcoulomb of charge to give it, suppose you want to change it to a positive 2.3 microcoulomb. So how many electrons do we have to remove from this negative charge to make it a positive charge? So we have a change. And anytime you have a change, see that's the delta symbol, you have a change in charge, you need to just take your final charge, your 2.3, minus your initial charge, -1 microcoulombs, of course. And since your base equation is Q is equal to NE, you're not changing the actual constant, all right? The constant's not changing, just the number of electrons are changing. So really you're just doing a difference between the two numbers of charges. So that technically means you have delta N. That's what delta Q means. It's not the E that's changing, it's just the number of charges. So based on what we know our final charge, we know our initial charge, we're just looking for the number of charges that have changed over. So you can just manipulate the equation and subtract the 2 and divide by your constant. And it looks like this. 2.3 times 10 to the negative 6, because that's what a micro means. Coulombs minus the -1 microcoulomb, so 1 times 10 to the negative 6 coulombs. Just do that, you get 3.3, positive 3.3 times 10 to the negative 6 coulombs divided by your constant. And it just means you got about 21 trillion, or 2.1 times 10 to the 3 charges were removed from the wool socks. Right? That's really all that means. Okay, I rambled too long. That's enough for today.